Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at gas solubility, and this is most famously described with Henry's law. So in trying to look at the solubility of a gas, one of the big things we're looking at is how well a gas like oxygen dissolves in water. And this is a very classically important reaction, as anything that lives in water tends to need a lot of oxygen, most famously things like fish and bacteria. So trying to figure out the levels of oxygen that can dissolve into these aqueous environments are really critical for understanding a lot of important biological life processes. So what we can do is we can do something similar as what we did for saturation. We can go ahead and look at our reaction. I'm going from gas to aqueous. And then I can go ahead and use this to build up an equilibrium constant. In this case, it's just going to be concentration, because that's how we describe an aqueous species, and pressure, because that's how we introduce a gas species. Now, the concentration will be given in molarity, and the pressure is most frequently given in bar. Now, because this forms our equilibrium constant, we also know that we can relate it to the Gibbs free energy of reaction. So if we end up knowing our Gibbs, we can figure out our equilibrium constant. However, it turns out that this equilibrium constant is so special that it receives its own name, and it's called the Henry's constant. And again, typically given as concentration over pressure, and that would give us units of molarity per bar, or occasionally molarity per atmospheres. However, one of the things I want you to be very aware of is that a lot of people tend to flip the units on this equilibrium constant, at which point it represents the reverse reaction of an aqueous species like oxygen end up volatilizing or producing a gas. So in this case, it would be pressure over concentration. And I apologize for the confusion in between these two, but it turns out you could always figure out which one is which by looking at the units. If it's molarity on top, your product is in the aqueous phase. If it's pressure on top, it means your product is in the gas phase. So as a result, always pay attention to the units and be very careful of where you get your equilibrium constants from, because about half of them are going to give the units on the top, and the other half are going to give atmosphere on the top. So using either one of these forms, we can end up describing very similar processes, like trying to figure out the level of oxygen in room temperature water. So again, worth noting, these equilibrium constants, or these Henry constants, are going to be temperature dependent. So for example, this value of 770 atmospheres per molar is going to refer to room temperature 25 degrees C water. So let's say I'm in a room with ambient oxygen levels. So that's about 21% of atmospheric pressure, or that would give a partial pressure of about 0.21 atm. So using this, I can figure out, rearrange the equation, put molarity on top, and move the Henry's constant to the bottom. Then using this, paying attention to units, we're going to find that our atmospheres end up canceling out, giving us molarity as units on the top. So yes, our oxygen concentration will have units of molarity of about 2.73 times 10 to the negative fourth molar. So for convenience, you could, this is often phrased in micromolar, or occasionally you can convert it to ppm, but again, be very careful because it's moles per liter and not some other type of metric. So if I'm looking at room temperature water, the maximum amount of oxygen, so if I'm actively, putting one of those fish tank aerators in there, is going to end up being about 27 micromolar, which isn't a lot of oxygen. But for a lot of fish, this is the maximum level of oxygen they have to work with, which ends up showing a lot about how well fish can end up moving oxygen through their blood and systems as they're able to survive on these fairly low levels. However, it turns out that some fish need more and some fish need less oxygen than this mark. And it turns out that one of the reasons why is the favorability of how much oxygen I can get into water changes with temperature. And we can determine exactly how much it changes with temperature by, not too surprisingly, knowing the enthalpy of reaction, because as we saw last time, enthalpy will control favorability with temperature. And we can depict this mathematically by starting with our Henry's constant. It will be based on a Gibbs free energy of reaction. And in this case, we know that what we can do is replace our Gibbs free energy with enthalpy minus temperature times entropy. So this is our classic relationship here. However, we then want to go ahead and split this up. So we can move RT over on this first side and on the back side by distributing this 1 over RT. So this gives us an exponential times negative enthalpy over RT plus entropy over R. And because we're looking at temperature dependence, what we're going to do is pull out all the temperature dependence out front and leaving the entropy behind. Again, using the log rules or exponential rules, as adding two exponents together is the same as multiplying the exponentials times each other. Now, because it's nice if we can draw a more linear relationship, we're going to take natural log times the whole thing. So this gives us the natural log of Henry's constant is going to be equal to negative enthalpy over RT plus entropy over R. Now, one of the things I want to point you to is that this will look rather familiar to us because this was a very similar equation we saw for the Clausius-Clapeyron behavior when we were looking at vapor pressure instead of partial pressure or equilibrium constants. And as a result, you can actually end up with a very similar sort of linear behavior, as the natural log of the ratio of your new Henry's constant versus the old one can be given as negative of the enthalpy over R times the difference of 1 over new temperature over old. So using this, what we can end up doing is determine the solubility or Henry's constant for a gas at any new temperature. And one of the useful things here is that we know that for the solubility of a gas, this process will always be exothermic. The gas will always have better IMFs in the aqueous phase than it does on its own, as demonstrated by oxygen having a value of negative 21.1, which is fairly typical. So because this is an exothermic process, what ends up happening is the solubility of the gas tends to increase at lower temperatures. And again, we saw this with the basic idea. If I put in more energy, it will end up favoring the more disordered phase, in this case, oxygen. However, it is worth noting we've got a lot of inverse temperatures here and a lot of negatives, which really tends to ruin our mathematical intuition of this behavior. So let's go ahead and try and figure out a real problem. So we know the solubility of oxygen at room temperature. However, turns out there's a lot of fish that live in water that is near freezing, so about 273 Kelvin. So let's figure out what the Henry's constant is for that condition. So in this case, what we can end up doing is rearranging the equation to solve for our new Henry's constant using the old one and the two different temperatures. We plug in all of these values and we get lucky here because enthalpy is negative, which cancels out the negative here. And then we just plug in old temperature, new temperature, remembering your enthalpy. So when we do this, if we've determined that our original Henry's constant, which we determined previously, was 0.00128 molar per bar, our new Henry's constant is 0.002. Note that this is almost twice as high. And this means that you can get almost twice as much oxygen in ice cold water as in room temperature water. And one of the reasons why this is so important is this tells us a lot about why you have things like cold water fish and warm water fish. Warm water fish are designed to survive with lower concentrations of oxygen. Cold water fish need much higher levels of oxygen. So as a result, big fish need more oxygen, and so they tend to live in cold waters. So think Arctic waters or lakes up north. As you move further to the south, you either end up with much smaller fish or fish like catfish, which use a lot less energy and can survive on lower oxygen levels. So it turns out this explains a lot of the biology of oceanic and even freshwater species. However, next time we're going to be trying to flip the script, and we just looked at what the vapor pressures or solubility of a dissolved gas is Next time, we're going to be looking at the vapor pressure or amount of gas of the solvent above a mixed species. So this time we figured out how much water or air was in the water. Next time, we'll figure out how much water is in the air. Until then, take care.